In mathematics, a sequence is an ordered collection of objects in which repetitions are allowed. Like a set, it contains members. The number of elements is called the length of the sequence. Unlike a set, order matters, and exactly the same elements can appear multiple times at different positions in the sequence. Formally, a sequence can be defined as a function whose domain is a countable totally ordered set, such as the natural numbers. For example, is a sequence of letters with the letter M first and Y last. This sequence differs from, also, the sequence, which contains the number 1 at 2 different positions, is a valid sequence. Sequences can be finite, as in these examples, or infinite, such as the sequence of all even positive integers. In computing and computer science, finite sequences are sometimes called strings, words or lists, the different names commonly corresponding to different ways to represent them into computer memory. Infinite sequences are also called streams. The empty sequence is included in most notions of sequence, but may be excluded depending on the context. Examples and notation. A sequence can be thought of as a list of elements with a particular order. Sequences are useful in a number of mathematical disciplines for studying functions, spaces, and other mathematical structures using the convergence properties of sequences. In particular, sequences are the basis for series, which are important in differential equations and analysis. Sequences are also of interest in their own right and can be studied as patterns or puzzles, such as in the study of prime numbers. There are a number of ways to denote a sequence, some of which are more useful for specific types of sequences. One way to specify a sequence is to list the elements. For example, the first 4 odd numbers form the sequence. This notation can be used for infinite sequences as well. For instance, the infinite sequence of positive odd integers can be written. Listing is most useful for infinite sequences with a pattern that can be easily discerned from the first few elements. Other ways to denote a sequence are discussed after the examples. Important examples. There are many important integer sequences. The prime numbers are the natural numbers bigger than 1, that have no divisors but 1 and themselves. Taking these in their natural order gives the sequence. The study of prime numbers has important applications for mathematics and specifically number theory. The Fibonacci numbers are the integer sequence whose elements are the sum of the previous 2 elements. The first 2 elements are either 0 and 1 or 1 and 1, so that the sequence is. Other interesting sequences include the Ban numbers, whose spellings do not contain a certain letter of the alphabet. For instance, the Eben numbers form the sequence. Another sequence based on the English speaking of the numbers is the one based on their number of letters. For a list of important examples of integer sequences, see Online Encyclopedia of Integer Sequences. Other important examples of sequences include ones made up of rational numbers, real numbers, and complex numbers. The sequence approaches the number 1. In fact, every real number can be written as the limit of a sequence of rational numbers. It is this fact that allows us to write any real number as the limit of a sequence of decimals. For instance, pi is the limit of the sequence. The sequence for pi, however, does not have any pattern that is easily discernible by eye, unlike the sequence. Indexing. Other notations can be useful for sequences whose pattern cannot be easily guessed, or for sequences that do not have a pattern such as the digits of pi. This section focuses on the notations used for sequences that are a map from a subset of the natural numbers. For generalizations to other countable index sets, see the following section and below. The terms of a sequence are commonly denoted by a single variable, say m, where the index n indicates the nth element of the sequence. Indexing notation is used to refer to a sequence in the abstract. It is also a natural notation for sequences whose elements are related to the index n in a simple way. For instance, the sequence of the first 10 square numbers could be written as this represents the sequence. This notation is often simplified further, as here the subscript k equals 1 and superscript n together tell us that the elements of this sequence are the ACK such that k equals 1, 2, 10. Sequences can be indexed beginning and ending from any integer. The infinity symbol infinity is often used as the superscript to indicate the sequence including all integer k values starting with a certain one. The sequence of all positive squares is then denoted in cases where the set of indexing numbers is understood, such as in analysis. The subscripts and superscripts are often left off. That is, one simply writes ACK for an arbitrary sequence. In analysis, k would be understood to run from 1 to infinity. However, sequences are often indexed starting from 0, as in some cases the elements of the sequence are related naturally to a sequence of integers whose pattern can be easily inferred. In these cases the index set may be implied by a listing of the first few abstract elements. For instance, the sequence of squares of odd numbers could be denoted in any of the following ways. Moreover, the subscripts and superscripts could have been left off in the third, fourth, and fifth notations if the indexing set was understood to be the natural numbers. Finally, sequences can more generally be denoted by writing a set inclusion in the subscript, such as in the set of values that the index can take on is called the index set. In general, the ordering of the elements ACK is specified by the order of the elements in the indexing set. When n is the index set, the element ACK plus 1 comes after the element ACK, since in n, the element comes directly after the element k. Specifying a sequence by recursion sequences whose elements are related to the previous elements in a straightforward way are often specified using recursion. This is in contrast to the specification of sequence elements in terms of their position. To specify a sequence by recursion requires a rule to construct each consecutive element in terms of the ones before it. In addition, enough initial elements must be specified so that new elements of the sequence can be specified by the rule. The principle of mathematical induction can be used to prove that a sequence is well defined, which is to say that every element of the sequence is specified at least once and has a single, unambiguous value. Induction can also be used to prove properties about a sequence, especially for sequences whose most natural specification is by recursion. The Fibonacci sequence can be defined using a recursive rule along with two initial elements. The rule is that each element is the sum of the previous two elements, and the first two elements are 0 and 1, with then the first 10 terms of this sequence are 0, 1, 1, 2, 3, 5, 8, 13, 21, and 34. A more complicated example of a sequence that is defined recursively is Recursive sequence, considered at the beginning of this section. We can define Recursive sequence by n if the result is positive and not already in the list. Otherwise, not all sequences can be specified by a rule in the form of an equation, recursive or not, and some can be quite complicated. For example, the sequence of prime numbers is the set of prime numbers in their natural order. This gives the sequence. One can also notice that the next element of a sequence is a function of the element before, and so we can write the next element as. This functional notation can prove useful when one wants to prove the global monotony of the sequence. Formal definition and basic properties. There are many different notions of sequences in mathematics, some of which are not covered by the definitions and notations introduced below. Formal definition: a sequence is usually defined as a function whose domain is a countable totally ordered set. Although in many disciplines the domain is restricted, such as to the natural numbers. In real analysis, a sequence is a function from a subset of the natural numbers to the real numbers. In other words, a sequence is a map F, N, R. To recover our earlier notation, we might identify n equals F for all n or just write an N, R. In complex analysis, sequences are defined as maps from the natural numbers to the complex numbers. In topology, sequences are often defined as functions from a subset of the natural numbers to a topological space. Sequences are an important concept for studying functions and, in topology, topological spaces. An important generalization of sequences, called a net, is to functions from a directed set to a topological space. Finite and infinite. The length of a sequence is defined as the number of terms in the sequence. A sequence of a finite length n is also called an n-tuple. Finite sequences include the empty sequence that has no elements. Normally, the term infinite sequence refers to a sequence which is infinite in one direction, and finite in the other. The sequence has a first element, but no final element. It is called a singly infinite, or one-sided sequence, when disambiguation is necessary. In contrast, a sequence that is infinite in both directions, i.e., that has neither a first nor a final element, is called a bi-infinite sequence, two-way infinite sequence, or doubly infinite sequence. A function from the set Z of all integers into a set, such as for instance the sequence of all even integers, is bi-infinite. This sequence could be denoted. One can interpret singly infinite sequences as elements of the semigroup ring of the natural numbers Rn, and doubly infinite sequences as elements of the group ring of the integers Rz. This perspective is used in the Cauchy product of sequences. Increasing and decreasing. A sequence is said to be monotonically increasing if each term is greater than or equal to the one before it. For a sequence, this can be written as an n plus 1 for all nn. If each consecutive term is strictly greater than the previous term, then the sequence is called strictly monotonically increasing. A sequence is monotonically decreasing if each consecutive term is less than or equal to the previous one, and strictly monotonically decreasing if each is strictly less than the previous. If a sequence is either increasing or decreasing, it is called a monotone sequence. This is a special case of the more general notion of a monotonic function. The terms non-decreasing and non-increasing are often used in place of increasing and decreasing in order to avoid any possible confusion with strictly increasing and strictly decreasing, respectively. Bounded. If the sequence of real numbers is such that all the terms, after a certain one, are less than some real number m, then the sequence is said to be bounded from above. In less words, this means an m for all n greater than n for some pair m and n. Any such m is called an upper bound. Likewise, if, for some real m, and m for all n greater than some n, then the sequence is bounded from below and any such m is called a lower bound. If a sequence is both bounded from above and bounded from below, then the sequence is said to be bounded. Other types of sequences. A subsequence of a given sequence is a sequence formed from the given sequence by deleting some of the elements without disturbing the relative positions of the remaining elements. For instance, the sequence of positive even integers is a subsequence of the positive integers. The positions of some elements change when other elements are deleted. However, the relative positions are preserved. Some other types of sequences that are easy to define include: an integer sequence is a sequence whose terms are integers. A polynomial sequence is a sequence whose terms are polynomials. A positive integer sequence is sometimes called multiplicative if a n m equals an m for all pairs n, m such that n and m are coprime. In other instances, sequences are often called multiplicative if n equals n1 for all n. Moreover, the multiplicative Fibonacci sequence satisfies the recursion relation n equals n-1 and -2. Limits and convergence. One of the most important properties of a sequence is convergence. Informally, a sequence converges if it has a limit. Continuing informally, a sequence has a limit if it approaches some value L, called the limit, as n becomes very large. That is, for an abstract sequence the value of n approaches L as n infinity. Denoted more precisely, the sequence converges if there exists a limit L such that the remaining n's are arbitrarily close to L for some n large enough. If a sequence converges to some limit, then it is convergent, otherwise it is divergent. If n gets arbitrarily large as n infinity, we write in this case we say that the sequence diverges, or that it converges to infinity. If n becomes arbitrarily small, negative numbers as n infinity, we write and say that the sequence diverges or converges to minus infinity. Definition of convergence for sequences that can be written as with an or we can write with the indexing set understood as n. These sequences are most common in real analysis. The generalizations to other types of sequences are considered in the following section, and the main page limit of a sequence. Let be a sequence. In words, the sequence is said to converge if there exists a number L such that no matter how close we want the n to be to L, we can find a natural number n such that all terms are further closer to L. This is often written more compactly using symbols. For instance, for all epsilon greater than 0, there exists a natural number n such that L minus epsilon less than and less than L plus epsilon for all n. In even more compact notation, the difference in the definitions of convergence for sequences in complex analysis and metric spaces is that the absolute value, n minus L, is interpreted as the distance in the complex plane. Sequences of real numbers include the following. These equalities are all true at least when both sides exist. For a discussion of when the existence of the limit on one side implies the existence of the other, see a real analysis text such as can be found in the references. The limit of a sequence is unique, provided if n be n for all n greater than some n, then if for all n greater than n, and then if a sequence is bounded and monotonic, then it is convergent. A sequence is convergent if and only if every subsequence is convergent. Cauchy sequences. A Cauchy sequence is a sequence whose terms become arbitrarily close together as n gets very large. The notion of a Cauchy sequence is important in the study of sequences in metric spaces, and, in particular, in real analysis. One particularly important result in real analysis is Cauchy characterization of convergence for sequences. In the real numbers, a sequence is convergent if and only if it is Cauchy. In contrast, in the rational numbers, e.g., the sequence defined by x1 equals 1 and xn plus 1 equals xn plus 2, xn, 2 is Cauchy, but has no rational limit, cf. here. Series. A series is, informally speaking, the sum of the terms of a sequence. That is, adding the first n terms of a sequence forms the nth term of another sequence, called a series. Thus the n series of the sequence results in another sequence given by. We can also write the nth term of the series as then the concepts used to talk about sequences, such as convergence, carry over to series, and the properties can be characterized as properties of the underlying sequences in the last example.